and Giuseppe Abreu, that they are currently in Japan, so they couldn't be here. I gave on behalf. So what we are talking about? Let's consider a typical downtown urban environment. So this is Chicago. So many tall buildings. So it's natural link to the first presentation that we had from Frederick. And let's consider just one road described with the ellipses. And yes, what happens there? That the GNSS is not everywhere. The signal from satellite is not perfect everywhere. We are not in line of sight situation. So we have peripheral cars that are at the end of this urban canyon or urban canopy, as you want. Have quite good, maybe not perfect, position estimate, because they can see most of the satellite necessary to get an accurate position. But the more we move in the center of this canopy, we basically lose the GPS or the GNSS signal, and so they cannot be located. What's the simple idea that we are going to analyze here is, okay, let's get this car at the peripheral zone, that they have acceptable level confidence on their own position due to GNSS, and then they can transmit position to the other. So they can hope, and they can rely they can be function as kind of anchor in order to let the guys inside to be located, self-located better. Yeah, that's the same picture of before. As I've seen, there is some path, not regular, because there could be something blocking the direct line, so it's not straight. But given that we are kind of urban canopian, it's not very regular. And let's proceed with some definition. So we have n vehicles in a eta-dimensional space. We describe with theta the coordinate of the unknown, and with unknown vehicle or vehicle that they cannot estimate their own position, unknown, and with A, with the pedix for the anchor. So cars or vehicles that they have enough GPS, enough GNSS signal. And then something important is this sigma k is a covariance matrix describing for the anchor the quality of the signal from the GNSS, because we know that it's still subject to some error. So our scenario, car at the borders, they get GNSS with some error described by this matrix, and they trying to send to the target theta that don't get almost any signal. Very simple model. We have distance with the distance has a Gaussian error, and the variance is subject to a path loss. That means it's better to jump from car to car instead than doing a long hop, because the longer the hop, the bigger is the attenuation, so more unreliable is the signal. And then we just accumulate the distance up to up and the error up to up. So when we have to hop between many cars, even though we can do the direct jump, it's better doing short steps. That's the message. And we want to estimate at the end of the day the performances of the possible location with the well-known Kramer-Rao lower bound that relates the covariance metric with the inverse of the Fisher. The traditional formulation, something new that we are adding, is that the anchor uncertainty is not considered. But now we want to do it in a different way also to allow us to consider the anchor uncertainty is to get the Fisher information, not doing element by element. That could also be quite challenging for many tasks, but using these so-called information vectors that are based on the distance and the position of the anchors with respect its target. So if we can build this UK vector, we can just have a formulation. This is algebraic, it's nothing new. We can just have a formulation of the Fisher. We want to go a bit more because our goal is anyway to get also to introduce the anchor uncertainty. We have an augmented parameter vector where we don't consider anymore only the target, but we put inside also the position of the anchors. And we get a bigger omega sigma that is anyway related in the same way to the inverse of the Fisher. Or better, we will try to get this Fisher theta. This Fisher information matrix can be approximated by two components. One given is the Fisher due to the anchor uncertainty, and one from the cooperation for the multi-op. And now we have, following the same logic as before, instead of having a UK, now that we are considering also the anchor position, we have this VK, and this is the just the definition, the mathematical definition. Yeah, and well noted, this is also only whenever the error on the anchor is relatively small, because if we have totally crazy error on the anchors of the car of the border, of course, doesn't make sense to cooperate at all. We go a bit, go back. So while this comes from the signal itself, because it must not be calculated, it's given or estimated. Each car anchor must estimate its own sigma and then the Fisher. This one we can compute in this simple way. We take the augmented vector, we do this product with the transpose, and we have a matrix that has this shape described in the following. But we are not yet there. Once we get the FM, as I said, the Fisher of the sigma is basically 0, 0, 0, and the inverse of the sigma, estimated, self-estimated. And finally, we get the Fisher big theta is the product A, B transpose B, and the C coming from the contribution from the multilateration, from the multi-op, and the contribution given by the error uncertainty. Now this is still, it's considering all the targets and all the anchor. It's a bit too much. We want to get the Fisher of the single car that he wanna estimate its own bounds. So in order to extract the component relative to the single star, Fisher star of theta, we can do a decomposition with the Schur complement. It's a bit heavy of math, but it's not really something magic. It's just a bit of time writing, but not complicating. It's a very simple Schur component, and we can get to the final formulation where the Fisher associated to the single target or vehicle that we want to estimate is given by this formula. This formula here, and it's good now because the anchor uncertainty now appears as a reduction of the information intensity. Information intensity was the vector F that we saw before, and now we can use this formula to do some analysis to consider what is the impact, what is the error due to the anchor uncertainty, and what is the anchor error due to the hopping, because we introduce some error. Just, I'm close to the end. I'm going fine with the time. We consider both one-dimensional and two-dimensional scenario. One-dimensional because, as I said, when we have these urban canyons, very long and not so wide, so we don't have highways in the middle of the downtown cities. We can approximate with one dimension, but we provide also for two-dimensional road. 500 meters long and 10 wide. Only vehicle at the border can self-localize themselves via GNSS. And each vehicle can range up to 70 meters, but of course they will select the best propagation route. So as I said before, they will prefer anyway to the path that will minimize the total error accumulation. And we want to see how good is the GNSS propagation through the network. Quite surprisingly, for such a big scenario like a road 500 meters, we have car just in the middle with a standard deviation of approximately, in the worst case, 3 meters. That's not too bad for a car that has no at all GNSS reception. Of course, it's not good like cars that are close to the border, that they can have good estimate, but it's not worst, not the worst scenario. And another thing to consider, that even in the case when we have perfect GNSS estimation, here it's GPS, the performance in the middle are pretty the same. So it's not so important in this urban canyon to have very accurate initial estimate of anchors, because they can have a pretty high with a star error, self-estimation error, or they can be even perfect, but at the end of the day, in the middle, this error is mitigated, or let's say it's secondary with respect to the propagation. This is another case, but instead of considering the GNSS error, we're just considering the signal-to-noise ratio. And in the case when we have very good signal-to-noise ratio, that's not even so exceptional level, it's SNR 10 dB. We are below the 2 meter of standard deviation. And with very poor SNR, we go at 5. There is another, here it's the bidimensional case analysis, where we basically forget to plot, instead of the ellipses, we plot only the error on the x dimension, because we are not so interested in this case to know if the car is here or here. It's only enough in this kind of emergency situation to understand on which part of the road is the car. And as we can see, this is still 500 meters. So basically what happens, those are anchors and those are target. The analysis indicates that they don't overlap, and they can pretty good still estimate their own position. It will not be sufficient for maybe for self-driving, but to not getting lost in urban environment, in order to know when you have to turn right or left, that you are in proximity of a very important junction. Only the multi-op communication, no other assistance technique or sensing information is pretty enough to estimate and get your own position. Yeah, this is why the huge error in the y-axis is just because of the error ellipsis. As I said, we can really forget and fly over this. That's all. Thanks.